This is Precalculus Concept 34C. We're going to talk about the law of sines in a special case called the ambiguous case. And this involves triangles where the given information is in the combination of side-side angles. So you may remember from geometry that side-side angle is not enough to guarantee the two triangles are congruent to each other. And this is basically a little bit further explanation of why. So down here in red I have an example of a triangle where angle A, and side C are kind of these fixed lengths. And the way I've drawn it, it seems like maybe that's the only triangle you could draw. But the fact that angle B is not fixed up here, means that A could kind of swing freely, and if you imagine there might be a different place where A could be. And notice that the length of A, the length of C, and the size of angle A have not changed. And yet I have two completely separate triangles. So if you draw those out, there's one triangle that looks like this, and there's the other triangle that looks like this. Both of them have the same angle A, both of them have the same side C, and both of them have the same side A. And so this is one example of where side-side angle does not necessarily yield just one triangle. As it turns out, there's kind of three different cases in this scenario. We're going to break them down on the next slide. Alright, so I've drawn the same triangle three different times, and we're going to basically change side A slightly. So in our first example, we're going to let A be 2. Alright, so I'm going to draw in a side of length 2, and just think about what happens. So it turns out that the law of sines is going to kind of reveal what happens in every case, so that's going to help us out quite a bit. So I'm going to do the sine of 40 over 2, and I know that that's going to be the side of angle C over 10. When I solve this, I'm just going to multiply both sides by 10, and so I get 10 sine 40 over 2 equals sine C. And when I pull my calculator out, it turns out that sine C is equal to about 3.2. Right? At this point, if you want to find the value of angle C, you would have to do the inverse sine of 3.2, and hopefully you'd recognize right away that I'm going to have a problem with that. There is no such angle whose sine is 3.2, and so there's no solution to this. If I go back up to my picture, what I've basically encountered is a scenario where the side there, 2, is too small to create a triangle, and if I drew that to scale, it would kind of make sense that, the length 2 is actually not going to reach. So sometimes with side-side angle, you end up with no solution or no triangle. Alright, let's take a look at 8. Alright, this is case 2. I'm going to start off with the law of sines. So sine 40 over 8 equals sine C over 10. And once again, if I find sine C, that's going to be an expression, in this case 10 sine 40 over 8. And the decimal I get this time is about 0.803. This time when I do inverse sine on my calculator, I will get an answer, and the measure of angle C turns out to be about 53.5. Here's what's really important to remember with the ambiguous case, is that there is a second answer that your calculator doesn't tell you. And you've talked about this before previously, that if I'm thinking about a trip around the circle, there are actually two places where the sine would equal 0.803. Your calculator only gives you one of them, and so the other one I'm going to figure out by doing 180 minus. So let me put that in yellow here. 180 minus 53.5 would give me the other angle, and that in this case turns out to be about 126.5. Okay, if I go back up to my picture, this is the thing where you can imagine that 8 length kind of swinging, and it could create an angle C that's an acute angle, so that's the one that's 53.5. I'll write that in here. Okay. Or it could also create an obtuse angle, and that's the one that's 126.5. And from this point on, I have two different triangles, and I want to solve them both. And so I still have some work to do. I can figure out angle A by taking 180 and subtracting the other two angles. So the first angle that was given was 40, and the second angle that was given was 53.5. And so angle A turns out to be, I think, 86.5 here. Okay, and so that's kind of the first case, right? The second case for angle A would be to do 180 minus the two angles. One of them is still 40, but now my second one is 126.5. Right, and that ends up being 13.5. Okay, so basically for the rest of the problem here we have these two separate triangles and I have to solve all the pieces for both. The last step here would be to figure out side A, and we're going to go back to the law of sines for that. So I'd have the sine of 86.5 over A equals the sine of 40 over 8. And I'll do the math for you on that one. A turns out to be about 12.4. And in this one, I would set it up as the sine of 13.5 over A equals the sine of 40 over 8. A turns out to be 2.9. So there's a lot of work in this two-case scenario. But the number one thing, the most important thing here is to remember in this step where you're solving that there are actually two answers for angle C, and therefore there are two resultant triangles. Alright, let's look at case 3, which is a little bit easier. Let's pick a length like 12. So I'm going to pick 12 for my C. So I have sine 40 over 8 equals sine C over 12. Sine C is going to be 12/8 times the sine of 40, and in this case that turns out to be about 0.54. And angle C then is going to be the inverse sine of that, which is 32.4 degrees. Or, and again I have two possibilities, 180 minus that. So 180 minus that turns out to be, one second here, 180 minus 32.4, 147.6. Okay, in this scenario, when I move on to my next step, finding angle A, I'm going to do the same thing. I'm going to do 180 minus, the sum of the two other angles, which is 32.4 and 40. And when I do that, I get my angle A, which is 107.6. Okay, and for the other case, if I try 180 minus 147.6 plus 40, you may realize right away that you're going to get a negative answer here. And so there are times when you use the law of sines that second scenario doesn't end up working out. And it won't be apparent until you actually kind of work it through and figure out the answers there, but the second case here ends up not working. Okay, and so there is no second triangle. This one there is only one solution, and we can go on to figure out, sorry about that, side A with the law of sines, and I'll just jump to the answer here, which is 17.6, or 17.8 rather. Okay, so when you have the long and short of it here is that when you have side-side angle, there are three cases. There's one case where there is no triangle, there's one case where there's two triangles, and there's one case where you only have one triangle. And there's no real obvious way at the beginning to know, but the law of sines kind of reveals the situation. Alright, let's try another example here. I'm going to give you three things and ask you to come up with the solution to the triangle. So I'm going to draw out a triangle where one angle is 70 and the side across from that is 15, and then you have another side that's 13, and that we'll call that across from angle C. So the law of sines is how I'm going to start this problem. I know that the sine of 70 over 15 equals the sine of c over 13. And when I cross multiply, the sine of c equals 13 sine 70 over 15. And that turns out to be about, I didn't do my decimal here, let's do that real quick, 13 sine 70 over 15, 13 sine 70 divided by 15, about 0.814, oops. Okay. And when I find angle C, I'm going to do the inverse sine, and I get 54.5, or I also get 180 minus that, which is 125.5. Okay, when I go on to find angle A, that's going to be at the top of my triangle here, I have to kind of think about both cases. So if I add 70 and 54.5, and I subtract that from 180, I get angle A, which is 55.5. Okay, or my second case would be 70 plus 125 subtracted from 180, but that's going to give me a negative result. And so this is an example where that second case doesn't work. So this is one of my one triangle cases. And again, you don't know that until you get to that step down there where you're trying to find the third angle, and it doesn't make sense. Alright, my last step in this one would be to find side A. So I know that sine 70 over 15 equals the sine of A over A. In this case, I know that angle A, so that's going to be the 55.5 over side A. And using your calculator and figuring that out, A turns out to be about 13.2. Okay, when you're asked to solve a triangle, you're finding all the missing pieces. So I'm now done with this problem because I've found the missing side A, the missing angle C, and the missing angle A. And we say that the solution is solved. Alright, let's finish up with a U-try. We're not going to make you go all the way through and solve this, but if I gave you these three pieces of information, could you find angle C? And I'm going to give you a hint here that there are two answers. Okay, so hopefully use law of sine, set it up, found sine of angle C equals 0.92, and realize that your calculator is going to give you one answer, but there is a second answer, which is 113.2. If I think about the third angle, 50 plus 66, there'd be a third angle to figure out, and 113 plus 50 is less than 180, so there'd be a third angle for this. So this is an example where if you continued the problem, there would be two different triangles.